Now, uh, hi, I start the next topic, that is joint distribution function. Okay, so the subtopic name is joint distribution function. The entire thing falls whatever I'm speaking for the last couple of videos, 3 to 4 videos. They are all on a discrete joint distribution. Okay, so this topic is joint distribution function. Um, so what it reads, let capital, please follow the page number 136. Okay, we are now going through page number 136. Please see the page number. All of you please traverse to that page. It's given as in an image, as an image in your WhatsApp group. So it is written, let capital X comma Y be bivariate. You know what is bivariate? Having joint probability masses Pij, where I is greater than equal to 1 and less than equal to M, and J is greater than equal to 1 less than equal to N. So we were already dealing with these datas and these limits already in the previous examples also. Okay, so it's nothing new for us. Then the two variable function. So we have now a two variable function which is called fxy. Okay, fx comma y. That is equal to what? This fxy is equal to, please follow this thing very carefully, p capital X greater than minus undefined less than equal to x, comma, capital Y again greater than minus undefined, minus infinity. Okay, this is not undefined, this is infinity, less than infinity, less than y. Okay, so please study this thing. I repeat it. Fxy is equal to fx comma y. This function is equal to probability of two terms. What are these two terms? I circle them, x and y. Okay, I circle the two terms, x, capital X and capital Y. So capital X is greater than, left hand bound is minus infinity and right hand side is small x. Okay, and capital Y, left hand bound is again minus infinity and right hand side is capital Y less than equal to capital Y. Okay, this is called as the joint distribution function or joint cumulative probability distribution of x and y. This is called as, you remember this thing, joint distribution function of x and bivariated. Okay, so capital X, small x y is equal to probability of capital X belonging to this range minus infinity to small x and capital Y minus infinity to small y. Okay, now let us find out the function fxx. Okay, I rub this thing. Means again the marginal distribution. Okay, you know, adding all the row values. So we will get f suffix x, then function of x, that is equal to, just look very carefully, you have to remember these things. Again we have capital X and capital Y, these are the two values. Okay, only the limits we have to check, that is equal to greater than minus infinity and less than equal to small x. Okay, and y greater than again minus infinity and less than plus infinity. Please check this thing. Okay, so fx is equal to probability of, again I circle x and y. Okay, probability of x and y, fx function of x, that is equal to probability of x and y. The limits for x are minus infinity to small x. Okay, and y is minus infinity to plus infinity. This is minus infinity, this is plus infinity. You follow the image, you will see it very clearly. Similarly, we will have now fy y, that is equal to again probability Now x is over here is minus infinity to plus infinity, and y over here is minus infinity to small y. Okay. If it is fxx, then you have to memorize it like this, that the value of x will be means from minus infinity to x, okay, and this will be from minus infinity to plus infinity because this is fxx. So for y it will only be from minus infinity to plus infinity. And fyy, this y will be from means over here we have y, okay, so this y will be minus infinity to y, but x, there are no terms of x, so x will be minus infinity to plus infinity. You have to remember this thing like that. Yes. So let us check this example. Okay. In this example we have CF12, that is equal to P. Again we are using this particular function, okay, joint distribution function, not the previous functions. This is joint distribution function. Capital X is greater than, so what we have, minus infinity, okay, to, and it is less than 1, okay, this is the value of small x, okay, and we have over here y's value is minus infinity to 2. So what are the values we can have over here? So x value has to be less than 1 and y's value has to be less than 2, okay. So we can have, for first let us calculate with x and then we will calculate it with y, okay. So x values also includes this particular one. So we can have p 1 comma 0 plus p 1 comma 1 plus p 1 comma 2 plus p 0 comma 0 plus p 0 comma 1 plus p 0 comma 2. So this p 0 comma 0 means that situation where both x and y are 0, because it is an x and y has to be, x value has to be maximum 1 and y's value has to be maximum 2. Means x value cannot cross 1, okay, and y's value has to be maximum 2. So both an x, if I don't take any x and y, then this condition is satisfied. Now x is 0, y is 1, x is 0, y is 2. Okay, so these are three correct conditions. Now let us see this x is 1, okay, because x value can be maximum 1. So in such situation again y's value is 0, x is 1, y's value is 1, x is 1, y's value is 2. Now you will say, ma'am, why not p20? Because by the condition it is given that x's value can be maximum 1. So you cannot put 2 over here. Okay, and y's values can be maximum 2. So we can have three combinations, 0, 1 and 2. Again 0, 1 and 2. And x value is only 0, 1, 0, 1, 0, 1. Okay, now you have to add up the probabilities and you will get a finally a value 49 by 60. Okay. So this is another example to demonstrate this for joint distribution function. How do we do this? Now, there is a theorem. Just have to remember this theorem. There is no proof required. So what this theorem states, for any two independent random variables capital X and capital Y, the joint distribution function fxy is equal to fxx dot fxy, okay, fyy. So we have just right now studied fx comma y. We have also studied fx x and fy y. We have also studied these two parameters. So for any two random variables capital X and Y, fxy is equal to, has to be product of these two. Okay. So fxx and dot fyy. So this is the theorem. Okay. So now we will move on to page 141 when we will have theorems on expectation. Okay. We have studied expectation in the last videos yesterday. You have to please go through them. Please don't expect me to repeat them. Okay. Okay. So rub this thing and start theorems on expectation. So page 141, what it is written, let capital X, Y be a bivariate, capital X and Y be a bivariate with joint probability. What is the joint probability? Pij, that is equal to P capital X is equal to Xi and capital Y is equal to Yj. We get the following results. So if we get, so theorem 1, what theorem 1 states? Theorem number 1, it states E x plus or minus y, that is equal to E x plus or minus E y. Now if you had x, y, z, w, whatever it is, then E x plus minus y, y plus minus z plus minus w, that is equal to E x plus or minus E y plus or minus E w plus or minus E z and so on. Okay. Here we are doing with two variables, but it is also applicable for n number of variables. So Ex plus minus y, that is equal to Ex plus or minus Ey. So this is theorem number 1. Okay. Now the next theorem, no proofs are required. Next theorem states that for a joint distribution of capital X and Y, E x y, that is equal to Ex dot Ey. Okay. For a joint distribution of x and y, Exy is equal to Ex dot Ey. But the converse is not true. Means Ex dot Ey may not be equal to Exy. Okay. This is applicable, but not the reverse. Now we have, this is my theorem 2. Now we have theorem 3 that states E, okay, K, this is K is a constant. Now we have a function phi, okay, x comma y, that is equal to, K will come out of this because K is a constant, then E of that function phi x y. Okay, I repeat this is my theorem 3. Theorem number 3. This was theorem number 2. Sorry. Yes, this is theorem number 2. Okay. So EK means E expectation of this particular function with a constant added. First the constant will come out and then we will have expectation of this particular function. Now how to find out expectation already explained in the last videos, previous videos. Okay. Next comes theorem number 4. Okay. For a joint distribution of x and y, Ek is equal to K, where K is a constant. This is theorem number 4. This is theorem number 4. Okay. For a joint distribution of x and y, Ek is equal to K, where K is a constant. Okay. So we have completed the theorems on expectations. Now we will study a new topic. Yes. In the next video, that is called as the covariance. Covariance is very important, guys, because covariance is also included in your means pattern recognition. Find out the covariant matrix for means distribution, joint distribution. Okay, density functions, other things.